Here we describe how we simulated mechanistic models of the actomyosin ring using molecular dynamics simulations. First, we coarse-grained the system so that actin filaments are modeled as chains of beads, with each bead representing two monomers. We linked beads by springs and assigned a bending stiffness to match with the filament's known persistence length of 10 microns. In this visualization, filaments of different polarities are represented by different colors. We model myosin as a chain of beads connected by springs with the actin-binding motor domains at the end, colored in red. In our simulations, myosin was modeled in a bipolar form, a unipolar form, or both. We model cross-linkers to consist of two actin-binding domains connected by springs to a central bead, and two cross-linkers of different lengths were modeled. To prevent the beads from overlapping, we implemented a volume exclusion effect to the system. The membrane was modeled as a sheet of beads, but it will be visualized here as a surface. To model cell wall growth, as the ring pulls the membrane inward, new materials is deposited to fill the gap, preventing the membrane from relaxing back. Note that in subsequent animations, we don't visualize the cell wall. To model interactions between actin and myosin, we simulated each step of the ATPase cycle explicitly. First, the myosin head binds and hydrolyzes ATP, changing the head angle from 60 to 120 degrees. Next, myosin binds to actin and, through the release of phosphate, undergoes a power stroke to pull on actin. Next, ADP is released, allowing myosin to bind ATP and release actin, starting the cycle over again. We model myosin to walk towards the actin plus end. Next, in a stepwise fashion, we determine the basic components needed to constrict the ring and membrane. We started by simulating a ring consisting of actin filaments of mixed polarities and bipolar myosin molecules. We included the membrane to prevent expansion, but it is not linked to the ring. In this case, the ring does not contract because local tension due to actin-myosin interactions is not propagated along the ring. We next added actin cross-linkers to the ring to help propagate tension from one filament to another. While the system can now constrict, the ring-like arrangement is lost and the membrane does not constrict because it is still not linked to the ring. To confirm that the ring can generate tension and constrict the membrane, we randomly tether actin filaments to the membrane if they are less than 30 nanometers away, a distance based on the thermographic data. With the membrane to ring connections in place, we saw that the system can now constrict the membrane. However, under these conditions, the actin filaments become highly bent, in contrast to the straight filaments we observed in vivo by tomography. We identified two causes of filament bending. First, a myosin molecule walking away from a cross-linked anchor point introduces a pushing force that can bend the filament. Since it is known that myosin binds preferentially to actin filaments under tension, we added a rule that binding occurs only if myosin is walking towards an anchor point. Second, a filament can become bent if it is cross-linked to two other filaments that are moving towards one another. To fix this, we hypothesized that if there is a large angle between cross-linked filaments, the cross-link will release with a higher probability. We also introduced cofilin activity, which is known to preferentially cleave filaments that are not under tension. At this point, we also implemented protein turnover to reduce bending. Actin depolymerization was modeled to occur at the minus end, and new actin filaments are added to the ring stochastically. Similarly, idle myosin molecules are removed and replaced stochastically. We did the same for idle cross-linkers, removing and replacing them stochastically. Now, by adding these rules to our model, we observe that during constriction, filaments were straighter, more like those seen by tomography. With these components and rules in place, we next explore a variety of models for the ring. A prominent model suggests that actin and unipolar myosins are tethered to the membrane at nodes during ring assembly. We then started with this model, hypothesizing that this node may persist during constriction. However, nodes are not evident in our tomograms, necessitating the exploration of other arrangements. For actin, we explore 4 scenarios. In the first one, actin is tethered to the membrane-bound nodes. In the second, individual actin filaments are tethered to the membrane via their plus end. In the third, filaments are tethered randomly along their lengths. And in the fourth, actin is not attached to the membrane. Similarly, we explored 4 arrangements of myosins. First, unipolar myosins attached to membrane-bound nodes. Second, unipolar myosins attached to the membrane in pairs. Third, unipolar myosins attached to the membrane individually. Fourth, myosins are bipolar and not attached to the membrane. Together, this leads to 16 actomyosin combinations, but we know that the last one isn't plausible because the ring would not be connected to the membrane. For each simulation, the system started with a membrane section 300 nanometers wide and 2 microns across. We modeled 400 actin filaments of mixed polarities with an average length of half a micron and either 800 bipolar or 1600 unipolar myosins, and we added 1600 actin cross-linkers to the system. We first explore model 1, where both actin and unipolar myosins are connected to the membrane via nodes. We observe that nodes concentrate constriction force and pull the membrane inward inhomogeneously, generating puckers. As a result, many filaments form a large angle with respect to the membrane, in contrast to our tomography on real cells showing that filaments are parallel to the membrane. The same phenomenon occurs in model 4, where actin filaments connected to the membrane at nodes are combined with bipolar myosins. Puckering also occurs in model 13, when actin is untethered but myosins are concentrated in nodes. Taken together, these results suggest that constricting the membrane only via nodes causes puckering defects that are not consistent with observations by electron cryotomography. In model 2, we found that distributing membrane-bound myosins in pairs mitigated effects of puckering from actin nodes, but small puckers still occur, which is inconsistent with the smooth membranes we observe at the leading edge of the septum in our tomograms. In model 5, where actin is individually tethered to the membrane at its plus end and myosins in nodes, we saw that the nodes cluster in larger aggregates. These aggregates then concentrate the constriction force of the ring and deform the membrane. In contrast, aggregation is not observed with fluorescence microscopy. The same problem occurred in model 9, where actin is tethered along its length, showing that free myosin nodes lead to myosin aggregation. In model 6, where actin is tethered to the membrane at its plus end and myosins are in pairs, we still see myosin aggregation, although it is more gradual. To understand this phenomenon, we analyze the cause more closely. In this visualization, membrane beads are in yellow, but the 2 beads attached to 2 myosin pairs are colored in green. As the pairs collide, static hindrance prevents them from moving past each other, and through a positive feedback mechanism, the aggregation becomes larger. The same aggregation defect is seen in other models of myosin pairs, including model 10, where actin filaments are randomly tethered along their length. And in model 14, where actin filaments are not tethered to the membrane at all. In model 8, where actin is tethered at its plus end to the membrane and interacts with bipolar myosins, we observe that distribution of membrane tethers become inhomogeneous, gradually leading to accumulation of myosin at areas with abundant tethers. In addition, areas with abundant tethers show deeper furrows, and areas with sparse tethers show shallow furrows. These attributes are mitigated to some degree in model 12, where actin to membrane tethers are abundant due to lengthwise tethering. In addition, we found that bundles of actomyosin occasionally peel off from the ring and become lost into the cytoplasmic space. This phenomenon has been observed experimentally by fluorescence microscopy. Also, more filaments are observed at a large distance from the membrane, closer to the distances measured in tomograms. In model 3, where each unipolar myosin is tethered individually to the membrane, we find that force is distributed homogeneously from the ring to the membrane, and the membrane constricts smoothly with no myosin aggregation. Unlike in tomograms, however, actin filaments are pulled very close to the membrane. The same is true for all the models involving individual unipolar myosins attached to the membrane, including model 7, where actin is tethered only at its plus end. Model 11, where actin is tethered randomly along its length. And model 15, where actin isn't tethered to the membrane at all, meaning that interactions with membrane-attached myosin alone confine actin filaments close to the membrane's inner surface. Informed by our model testing, we now propose a working model of the actomyosin ring. We believe that neither actin nor myosin is tethered in nodes because this results in puckering of the membrane, which we have not observed experimentally. We also think it unlikely that unipolar myosins is tethered in pairs, since this would lead to aggregation. While the presence of individual membrane-bound unipolar myosins can maintain membrane smoothness, it also confines filaments very close to the membrane, which is in contrast to the large very distance we observe in vivo. Therefore, we built and tested a model consisting of untethered actin and both bipolar myosins and individual unipolar myosins. In this model, the presence of individual unipolar myosins provides a necessary link between the contractile ring and the membrane while helping to maintain the membrane smoothness and circularity, and the ring constricts without obvious defects. Interactions between actin and bipolar myosin produce filament distances from the membrane that more closely recapitulate the in vivo data. In addition, we observe myosin segregation. Visualizing unipolar and bipolar myosins in different colors, we find they occupy outer and inner subdomains of the ring. This recapitulates a previous fluorescence microscopy observation that two fission East myosin II isoforms myo2P and MIP2P form larger and smaller rings. Further, actomyosin bundle loss is observed. When the ATPase rates of unipolar myosin are reduced, the interaction between actin and bipolar myosin becomes relatively stronger, and bundles of these two components frequently peel off. This is similar to what has been observed by fluorescence microscopy, that when the ATPase rate of myo2P was minimal, bundles of actin and MIP2P frequently peel off. In summary, the model that best recapitulates all experimental results to date, including our new images of the actin filaments in cryopreserved rings, comprises untethered actin and both unipolar and bipolar myosins.